We are going to solve application problems involving exponential growth and decay, and it's going to have some compound interest problems, population growth, and depreciation of an item over time. So let's start here with growth and decay applications. So basically, a real life quantity can either increase or decrease by a fixed percent each year or other time period. So the amount of the quantity after X years can be modeled by this equation. So you can see the one that increases has a plus sign in there, the one that decreases has a subtraction sign in there. A is the initial amount, so whatever that is, if it's a number of something or if it's a money value. And then R is the percent of increase or decrease written as a decimal. So some things will increase in quantity over time, and some things will decrease over time. So it might be a money object. A lot of things decrease in value, like cars do, but houses typically increase in value over time. So you might buy a house for $200,000, and in 10 years it might be worth $350,000, depending upon the market. So you can definitely increase over time. So there's a couple examples. So an example here, a machine is initially worth $30,000, but it loses 10% of its value per year. Find the value of this machine after 8 years. So it's losing its value over time, and so we're going to use that subtraction one. So let me write out the equation, and then we'll fill in the numbers. So that's the equation we're going to use because it's decreasing over time. It's losing 10% of its value each year. So 30,000 is what it was initially worth, so that's your A value. Your R is your percentage written as a decimal, so we're going to move the decimal point there 2 places to the left, and since there isn't one, it goes right after the 10. So our R value there is 0.10. And then X there is the number of years there, and that's just 8. So what I would do here is I would put it directly into my calculator just like that. So let me bring up my calculator here. I'm going to punch in 30,000. Oops, let me move this over. And then parentheses 1 minus 0.10, parentheses, caret key, 8 equals. And we get $12,914 and looks like 2 cents. So rounded in there, cent there, that 6 there is in the third decimal place. It's going to round that 1 up to a 2. So $12,914.02. All right, so then our next one here is we've got the cost of a car. It's also depreciating in value, so it's going down in value over time. So we're going to use that same formula again. So let's plug in everything we know. We know that the original cost of the car is $25,000. That's A. R is going to be 16% written as a decimal. And then X, we don't know that yet. That's just the equation. So our equation is just going to be terms of Y and X. And then in part B, we'll put a 5 in there for X. So there we have it. We've plugged everything in there that we needed to. So then in part B, how much will your car be worth in 5 years? X there being 5, so plug that in there, and then it says round to the nearest cent. So again, I'm just going to plug this right into my graphing calculator here, or just a regular calculator. It doesn't have to be a graphing calculator. So 25, 1, 2, 3, parentheses, 1 minus 0.16. Whoops. It's not 0.16. There we go. And then caret key. And then it's 5 years. Enter. So it's going to be $10,455 and near cent there. It's 0.29, but there's an 8 over there in the third decimal place. So it's going to round that 29 up to a 30. So we're going to have $10,455.30. All right, so we said we'd look at an item either appreciating or depreciating over a time. So now we're going to look at population growth. So population, a lot of times like in towns or in for different kinds of animals, a lot of times over time, they can increase. I mean, sometimes you have also a decrease, but we're looking at population growth. So this is what's going to model our population growth here. So this is what the formula there is. N of t equals n sub 0 times e to the RT power. The n sub 0 there, it's just a subscript there. You're just going to put a value in there for n sub 0 there. So it's going to be whatever the initial population. If they say there's 200 rabbits or 200 bacteria or 200 people or 200 wolves or 200 lynx, 200 squirrels, whatever it ends up being, that's your population at whatever time they decide to take that at. So over time, the population will go up and down for different things, for sizes of towns typically, for populations of animals. Typically they're trying to figure out the trend of it going increasing and things like that, when it's going to increase. So they'll use this population growth model to kind of figure some of those things out. So let's see what's going to happen here. So we have the initial size of the population there is n sub 0. R is a relative growth rate. Again, it's going to probably give you a percent, and then we're going to have to write that as a decimal and then plug that in there. And then time, it doesn't have to be number of years, but typically it is. Bacteria usually talks about the number of hours or the number of days. So it just kind of depends on what we're dealing with for the population there, that it would be growing so quickly. All right, so a population of 200 bacteria is growing at a rate of 15% each day. So we're going to write an equation that expresses the number of bacteria at time x. So I'm going to write down that formula. All right, so we're going to have n sub t equals the initial population there of bacteria is 2,000. Our R value there is 15%. Let's write that as a decimal. And then T there is our time. I mean, you could put an X up there. I'm going to use T. And so it says about how many bacteria will there be in 10 days. So 10 there being our T value. So let's plug that into our calculator here. So I've got 2,000 bacteria. The E button is right above the natural log button, so I had to hit second and then hit a LN button, and that gave me E to come up there on the screen there. And then I'm going to plug in 0.15 times 10. If yours doesn't superscript it like mine, you might have to put that inside parentheses if it just puts it off the side of the E. So we're getting 8,963. That 3 over there in the tens place is not going to round that up. So when we're talking about a population, we usually round it to the nearest whole number. And that's what it says in the instructions there too. So we're going to say 8,963 bacteria. All right, so let's do another population growth here. So now we've got these 50 rabbits. They are on a small island about 8 years ago. So the relative growth rate on the island is estimated to be 55% per year. In 12 years, what will the rabbit population be? So since it was 8 years ago that we started with 50 rabbits, and then we want to know an additional 12 years, that's a total of 20 years. We usually don't do a problem like this, but in this case, our T value is going to end up being 20. So A there is 50, and R there is 55% written as a decimal. So let's do that. R is 55%. Let's write that as a decimal. So that's 0.55 for R, and then times T, and we said that it had to be the 8 plus the 12. So let's plug that in. So I've got 50 E, so second ln, and then I've got 0.55 times 12. And I'm getting, oops, sorry, I wasn't supposed to put in 12, I was supposed to put in 20. All right, let me do that again. 50 second ln, 0.55 times 20. A lot of bunnies. So 2,993,707 over in the tens place at the 0, so that will not round the 7 up. So let's write that down. Notice I'm labeling my answers there. All right, so then we also said, so we've done population growth, we've done increasing or decreasing an item in value. And now we're going to look here at compound interest formula. We've got this A equals P times parentheses 1 plus R over N to the NT power. P being the initial investment, so whatever that is, it's usually some kind of value, $10,000, $1,000, $200, whatever that is. R being our interest rate, written as a decimal again. And then N, that's how many times it's being compounded per year. It's not going to tell you how many those times are. It's going to say it's compounded daily. So then you're going to have to know, oh, there's 300, how many times is that per year then? Well, there's 365 days of the year, so that'd be 365 goes into both of those ends. There's 2 ends in this problem. Weekly, there's 52 weeks in a year, so 52 would go in, if they say weekly, would go in for your ends. Monthly, there's 12 months in a year, so 12s would go in there for your ends. Quarterly, there's 4 quarters in a year, so 4 would go in for the ends, or I can think 4 quarters in $1. Semi-annually, that's twice, that's 2 times a year, so 2 would go in for the ends, and annually is just 1 time a year. So, and then T there equals the number of years. So Find the amount in which to which $1,500 will grow if deposited in a bank at 5.75% year interest compounded quarterly for 5 years. That's really nice interest. There's no way we're getting that kind of interest right now. So, but let's write out our formula. So again, P there being our initial investment, which is $1,500. R there being our interest rate, which is 5.75. And so we gotta move that decimal point over 2 places. So that becomes 0.0575. And then our N value, it says it's being compounded quarterly, so N there equals 4. Quarterly is 4 times. And then T there is simply 5 years. So let's plug that into our calculator. So again, I'm going to clear this out of here. So we got 1,500 parentheses 1 plus 0.0575 divided by 4 parentheses caret key, and you do 4 times 5 in your head and put in 20 there, or if there's a parenthesis following yours after this, because if you hit the caret key, sometimes it won't superscript it like mine. You might have to put this all inside of a parentheses. But I'm just going to go ahead and put down 4 times 5, or you could just say 20. So if you're not getting that value in there, you might want to change that 4 times 5 to 20. So again, round to the nearest penny, so $1,995.54 or 55 cents. And so third place over there is a 7. You're going to round that 4 up to a 5. Notice I'm labeling that with the $sign there, so we know it's money. So now we have another investment here. So write the equation out. A P there is initial investment, which is 30,000. R value there is 2% written as a decimal. And there is, it's compounded how often? Daily. If it's compounded daily, how many days are in a year? There's 365 days in a year, so that's your N value. And it doesn't, we're not going to put a T value in there yet, because for this one here, it just says write the equation. So I'm just going to say T. And I know it says y and x, but this is fine. This is the equation we're supposed to be using, so let's use it. So now let's come down here and let's say how much money will you have in the account after 6 years? 6 is going to go in for T. So again, we could put that into our calculator, and when I did that, this is what I got. $33,824.79. Right, and then we have this formula here. It's called compounded continuously. This is the last one we need to look at. So this one here, when it says it's compounded continuously, you're getting interest on your interest right away instead of it having to wait until the end of 24 hours like daily would, or at the end of every month, that would be monthly, you'd get interest on your interest, or at the end of every year, then you'd start getting interest on your interest. Compounded continuously is pretty much like almost like every second. So after every second, you're getting interest on your interest, and it's being that interest is going into your account and then you're earning interest for that. So that formula is A of t is equal to P times e to the RT power. So this problem over here says that in a bank at 4% interest compounded continuously, that's when you know you have to use this formula because it says compounded continuously. So the P value there is the amount, which is $10,000. R there is 4%, so write that as a decimal. And it says it's in there for 20 years, so times 20. So let's plug that into our calculator here. So I'm going to take 10,000, and then I'm going to get E, which is second ln. It's right above the ln button, and our R value there is 0.04. I'm going to say times 20 equals, and I get $22,255.40 or 41 cents. Well, there's a 9 over there in the third decimal place, so it's going to round that 0 up to a 1, so it's 41 cents. So there we have it. We can solve these application problems involving exponential growth, decay, including compound interest, population growth, and depreciation of an item over time.